Get ready to enter a brave new world with your host, Vasant Dhar.
For more color on the podcast and additional commentary, please subscribe to my newsletter at vasantdhar.substack.com. Hello, and welcome to Brave New World. My guest today is Nicholas Christakis, Sterling Professor of Social and Natural Science at Yale University, where he directs the Human Nature Lab. Nicholas is a sociologist and physician who has pioneered the study of how things like obesity, emotion, ideas, and germs spread through human networks. His groundbreaking research showed that weight gain can spread socially through close relationships and stimulated an entirely new field of inquiry into social contagion. His more recent work explores how AI agents can work cooperatively with groups of humans. Nicholas, welcome to Brave New World. Delighted to have you on the show.
Vasant, thank you so much.
So, Nicholas, you've been a pioneer in the area of, networks, social networks, human networks. So tell us a little bit about yourself, what influenced you growing up, what still influences you, and, just say a little more about yourself to the audience.
Well, it's hard to know where to begin. I mean, just to add a little color to your description of me as being interested in social networks, my lab studies, we call our lab the Human Nature Lab, and we're interested in that part of human nature that relates to our interactions with others that we express outside our own bodies. So, part of our nature might be, our capacity to take risks, or how human beings think, or individual level behavior, but we study sort of interpersonal behavior and human connection. So we study all aspects of that. We study phenomena like how groups form naturally, how we evolve to form these groups. We study the spread of things between individuals and groups, the spread of information, the spread of germs. Lately, we've been studying human hybrid machine human systems. So we've been studying what happens to human groups when you add AI. And you might wonder or ask, where did these interests come from? And maybe that's why you're beginning by,
Indeed.
Yeah.
In fact, I first heard about your work, the famous sort of Framingham database study, where if I were to sort of simplify it, one of the messages from that was that, if you hang around obese people, you get obese, so there's some sort of an influence, right? And that's what you were talking about earlier, that is, the spread of information or influence. And that got a lot of attention. And, you've taken that work forward in really several interesting ways. And I've been fascinating reading about it. But tell us about that. What was the genesis of that study, and what made you interested in that in the first place?
Well, that particular study, again, in the spirit of trying to give a kind of scientific autobiography, which I think is where you were going, there was a sequence of ideas, still to this day in my lab, every 5 years, I kind of make an intellectual move. We move into a new direction, and I try to stay 5 years ahead of the curve. I had grown up under the sword of Damocles. My mother was diagnosed with a very serious illness when I was 6 years old. And I grew up my whole life, my whole childhood, worrying that my mother would die. And she did eventually die when she was 47 and I was 25, by which time all three of my mother's sons had become doctors. We were a stereotypical family with a seriously ill parent that, all of us all the boys became doctors. I have two sisters as well. I went to medical school. But I had always sort of wanted to be a research scientist. And by the time I went to medical school in the 1980s, the era in which medical training alone was adequate to be a scientist was long gone. In the 50s and 60s, if you had an MD degree, you could do cutting-edge frontier science. But by the time I went to medical school, you really needed a PhD to do science, to be a scientist. You could, of course, engage in discovery as a doctor. You could do clinical research. There were other kinds of things you could do. But if you wanted to do sort of frontier science, you needed additional training, which I had not really realized. By the time I went to medical school, I had quite a few struggles in high school. My parents had gotten divorced. My family were immigrants from Greece. that's actually quite an interesting story in its own right. Both my parents were scientists. My father was a physicist. My mother was a physical chemist. They both came to the United States in the late 50s on Fulbright scholarships. They met through the Greek community in the United States. They both wind up at Yale Graduate School, believe it or not, as I said, in physics and chemistry. My mother, I think, was the only woman chemist in the whole department, in 1960, whatever that would have been, 1961 or something. And they met through the Greek community. They were married in the United States. But, they were immigrants. My mother eventually, soon thereafter, got seriously ill. My parents eventually got divorced. By the time I went to college, I had some exposure to scientists, like outside my family, but not enough to provide me enough guidance to, deflect me from medical school. So it was only in medical school that I discovered, damn, I also need a PhD. And I wound up, through a variety of serendipitous reasons, picking a PhD in a relatively low status field, namely sociology, for which in retrospect I feel blessed, actually, because it was via that field that I was exposed to social networks, which eventually became my life's work. But initially I was very much focused on sort of working through some of the challenges I suppose I experienced as a young person with a seriously ill parent. So my clinical focus was training to be a hospice doctor to care for the seriously ill, which I did into my 30s and 40s. I was I was a hospice doctor. I took care of seriously ill people. And in my research, initially, my dissertation was on the role of prognosis in medicine, was on the role of prognostication, how doctors make predictions, and specifically how non-clinical factors would have influenced physician decision-making in this regard, how beliefs in supernatural forces. One of the reasons doctors have historically avoided making predictions is because they believe that if they make a prediction, there might be a self-fulfilling prophecy, for example. Or they avoid making a prediction because they think it's a kind of arrogant arrogation of divine authority, for example. So I started that. So in the sort of early 1990s, I was studying prognostication. And then in the late 1990s, I became interested in sort of a shift in studying how to improve the care of the dying, because we have then and still now do a terrible job caring for terminally ill people in our society. Those among us who are terminally ill really lack political power, if you think about it. And, they can't march through the streets, advocating for what do we want? Better terminal care. When do we want it? Now. It's not, even though we are all going to die, and even though all of us know people who are going to die, and even though you would think we would all have an interest in improving care of the dying, unfortunately, it's not so great in our society. It wasn't then, it still isn't. Anyway, so I shifted into that. From prognosis, I moved into end-of-life care. And it was during that period of my life, in the 1990s, when I was an assistant professor at the University of Chicago, that I kind of happened on studying the widowhood effect, which is the dying of a broken heart, the increased probability of the recently bereaved to die. And I had some personal exposure to these ideas, these experiences of how illness can ripple through a family and affect other people. How the health status or well-being of one person might be affected by the illness status of someone else in the family. Obviously, this was something I had some experience with in my own life. By then, I had a PhD in sociology and my medical training. By the late 1990s, I was in my sort of mid-30s. And so I started studying. I had moved from prognosis to studying end-of-life care more generally and how to improve end-of-life care for the Americans. And then while doing that, I became interested in the widowhood effect. And I published a whole series of papers in the late 1990s on this effect, like how it works and how big is it and so on. And it was during that period of my life that I sort of realized at one particular moment that this thing that I had been studying, which is how death in one person might contribute to death in their spouse, actually was a special case of a much broader phenomenon, which was interpersonal effects more generally and social network effects. In fact, these effects are not restricted to dyads, I affect my wife, nor are they just restricted to death. I can affect my wife, who affects her sister, who affects her friend, who affects her coworker, can have these branching chains through the social networks, and not just about illness, by all kinds of other things, emotional states, obesity, you mentioned, various kinds of other behaviors. So I sort of made a shift in the late 1990s to studying social networks, and that became my life's work. Like since then, for 30 years, I've been studying different aspects of human interpersonal interactions, our embeddedness in social networks, why we evolved to have social networks, which is a very unusual phenotype as a species, what physiologic apparatus we are endowed with in order to select our friends. For example, when you're given a choice of 100 people, how do you like these 5 immediately and not like the others? There's a kind of physiology there that's quite interesting. What the structure of these networks mean for the flow of phenomena such as germs or ideas, how this relates to how the flow of ideas has shaped our evolution. In other words, one of the reasons you have friends and one of the reasons it enhances your Darwinian fitness is precisely because you can learn from your friends. And on and on and on and on. So that's 30 years. That set the stage for the rest of my life, if you will.
That's a fascinating and rich history, Nicholas. Thanks for sharing that. Truly remarkable how various kinds of phenomena spread in networks such as emotion, obesity, ideas, germs, and so on. I realized that we have several things in common, actually. My first exposure to AI in 1979 was through medicine when I saw an interaction between an AI system called Internist and an expert diagnostician. I start my book with that aha moment that led me down the path of AI as a PhD student. Listening to you describe the variety of social network phenomena that you've studied in your lifetime, I found myself asking, how do you pick the problems and projects that you want to work on?
Oh, that's a hard question. I
hadn't planned to ask it, but as you were talking, I was like, "Yeah, this is interesting." How do you really pick that?
There are a variety of axes by which I think and by which I would encourage any young scientist, and by which I imagine any other scientist operates when it comes to picking problems. First of all, I try to cultivate an open mind, and it's a self-discipline. I try to relax my mind and allow it to wander and permit it to make inductive leaps. So if I have crazy ideas, I try not to suppress them. I'd say, okay, contemplate that crazy idea. First point. Second point, I try to create a terrain that permits, chance favors a prepared mind. I try to allow for the role of serendipity. I try to cultivate or create the possibility of serendipity by mixing different disciplines in my laboratory. So we have physicists and sociologists and computer scientists and computational genomicists and anthropologists and doctors and all kinds of people in my lab. And I find that kind of cross-fertilization often leads to kind of kismet. You have a perfect interaction and you get some kind of new opportunity. I try to read broadly, so I try to read in allied areas, and this has gotten easier as I've gotten older because, by this time in my career, I have a big fund of knowledge. So the reading of something new in some marginal area adds a lot of value to a fund of knowledge that's already quite significant. Whereas if I had read the same thing when I was 30, I wouldn't necessarily have gained as much.
By the way, one of the major themes in my book is that very phenomenon of gaining so much more with AI if you know a lot already. The amplification of some humans with AI and the disempowerment of others.
Well, I mean, this notion that the rich get richer, is also true, and I also think, as you become more advanced as a scientist and as you've had a bit of success already, you can also afford to take more risk. So, if you're a PhD student or a postdoc, in your early 30s and your career rests on the success of your next project, it's a little bit harder to take that risk. But if you're further along, you can afford to take on riskier projects. And in fact, I generally encourage tenured professors to take on more risks. I think it's a bit of a travesty that more tenured professors don't take on more risks, not just lately politically, but also just scientifically. But, related to that, as I was about to say, that I also try to pick projects that are in the sweet spot of volume of other scientists working. So generally, it's risky, I think, to swim with sharks. One of the reasons my own lab, I was aware of the turn towards AI a bit early. I had some heads up from some entrepreneurs and some scientists. We in my lab, we published our first paper on AI in 2017 on how locally noisy autonomous agents can enhance global coordination in human groups. It's a paper we published in Nature in 2017. But the move I chose to make then was I realized I wasn't a computer scientist, and my lab really was not going to be able to be at the frontier in terms of studying the machine aspects, but we were going to be able to make a contribution in terms of studying the human aspects, how the machines are affecting the humans. And then last, I suppose, we have over the last few years, every 5 years, picked some new areas. Like we moved into the microbiome area. We moved into the AI area about 10 years ago. We moved into the microbiome area about 5 years ago. We've been moving into human social chemosignaling, 2 or 3 years ago. All of them build on a foundation, however, of deeply understanding human social interactions. So I'm still an astronomer and I'm looking at astronomical phenomena. I haven't moved to chemistry or biology, I'm still looking at, social interactions, but trying always to push the frontier as best I can, which to me is the most exciting thing about being a scientist.
So let's get into these areas, right? You mentioned, this experiment that you did, and I also want to get into your field experiments. But let's start with this study you did of hybrid kinds of systems, where you have people and then you insert an AI or an agent into those and what happens. So tell us about that, because I thought it was fascinating. I saw a talk you gave at ETH about this. So walk us through that thinking there and the general implications for, how we should think about designing these hybrid kinds of systems that have machines in them among humans.
Yes. So that's one of the more recent lines of work. And eventually we may come back to how that's connected to the work we do in these small villages in Honduras. But let's start with the AI work. So I guess to fix ideas, the kind of toy example I like to use to understand what it is that we are after when we are studying these hybrid systems of humans and machines is to ask listeners to think about what they want when they buy a digital assistant, like an Alexa device. You would never buy an Alexa if every time you had to speak to the Alexa, you had to say, excuse me, Alexa, I'm very sorry to interrupt you. If you don't mind, would you please tell me the weather tomorrow? This would be an absurd level of obsequiousness and politeness to the machine. You expect to be able to say, Alexa, weather, and the machine obediently responds. And that's exactly how the manufacturer designs that device. It's optimized for the individual human, individual machine interaction. And that's fine until you bring the machine into your home and your children in using that machine learn to be rude. And they go to the playground and they are rude to other children. So what my laboratory has been studying is human interactions in the presence of machines. How does the introduction of machines with particular kinds of programming that we modify, and I'll get to that, affect the collective performance of human groups by affecting how humans interact with each other? And our first paper, which we published in 2017, almost 10 years ago now, it's hard to believe, was in this regard. So what we did is we took a classic problem from computer science, which is called the graph coloring problem. And in the graph coloring problem, some people who are hearing this may remember the 4-color problem of maps. Like if you only need 4 colors. If you have any map of any set of countries in the world, you only need 4 colors available to you such that you can color every country with one color that is dissimilar than all of its neighbors' colors. And so the graph coloring problem is a problem in which you have a network. So a network has nodes, individual elements or people, and the connections between them and the ties, the little lines between the nodes. You can imagine in your mind's eye a network. Everyone is connected to certain other people who are in turn connected to certain other people. And we made networks like this, and we dropped human beings into these networks and introduced them to their new neighbors. And we told them, pick a color dissimilar from your neighbors. Now, we contrived for the network to have what's known as a chromatic number of 3. That means that, in fact, 3 colors were enough to solve the problem. In other words, from a choice set of 3 colors, if you put 30 people into this network, each person can pick a color dissimilar from their neighbors. That's their challenge. And you should have the intuition that, of course, if we gave them 1,000,000 colors, the problem would be trivial, right? Like just at random, 30 people picking 1 out of 1,000,000 colors, they would all have dissimilar colors from their neighbors. And also, if we only gave them 1 color or 2 colors, that clearly wouldn't be possible to solve the game. So 3 colors was the minimum number of colors necessary. We dropped the people into this network, groups of 30 people or so, and we timed how long it took them to solve the problem. So every minute or so that people look, every second or so, the people look at their neighbors and they say, "Oh, I'm orange. My neighbor is purple, green, and orange. I should switch from orange so I'm not in conflict with my orange neighbor. But if I pick purple, I'll be in conflict with my purple neighbor. On the other hand, I have only 1 purple neighbor. I have 2 green and 2 orange neighbors. I should just switch to purple. I'll minimize conflicts with my neighbors." So everyone in the group is trying to solve this coordination challenge. And sometimes they succeed and sometimes they don't. What we found was that if we surreptitiously replace some of the humans with bots, and if we endowed the bots with very simple artificial intelligence, specifically in this case that the bots occasionally made some crazy choices, some counterintuitive choices, what's known as adding a little noise to the system. So the bots increase the conflict with their immediate neighbors. Actually, that led to a global solution. It unlocked the ability of a group of people to solve the problem. And just if I might be allowed, another digression on this, just to fix ideas for listeners. This is actually this little description I've just given is very similar in broad swaths of the sciences. It has something to do with the origins of mutation, which you can think of as noise in biology, or the addition of platinum to organic chemistry reactions, which is a kind of catalysis, or simulated annealing or heat in chemical reactions. You agitate the system a little, and it allows the system to reach an optimal equilibrium. And social systems are the same way. And let me cultivate an intuition by asking listeners to imagine a broad field, a huge landscape, an enormous field with hills of different heights and a mountain. And I take 4 of you and I blindfold you and I handcuff you together so you're each facing in a cardinal direction, north, south, east, west, handcuffed, each looking in one direction, but blindfolded. And I tell this group of people, find the highest mountain. And you're like blindfolded and you're sitting there in some random spot on the field, this sort of so-called fitness landscape, this sort of Darwinian fitness landscape. And you say, okay, we're each going to take a step in our direction and report back, is it uphill? So north says it's uphill from here. South says it's downhill from here. East and west say it's lateral from here. So the whole group shuffles 1 step north. And you keep repeating this until you get to a point where everyone says it's downhill from here. So the question for listeners is, has this group found the highest mountain? And the answer is no. They've just found the nearest hill. Now, will they ever find the highest mountain? No, they won't. They're stuck. They're locally optimized, but globally suboptimized. They haven't found the highest mountain. And the only way they will ever get to the highest mountain is if you add a little noise. You perturb the system so that occasionally they can make counterintuitive downhill moves. Maybe they land back on the plateau. They keep exploring the fitness landscape, and eventually they find the highest mountain. And for various reasons, they tend to stay there. So the point here is that the programming of the artificial intelligence agent added to the human social system to have a little bit of noise helped the humans to help themselves. We showed that it was possible to increase the ability of groups of humans to solve a collective action problem, here a problem of coordination, by thoughtful programming of the artificial intelligence agents that were added to the system. And then from there, we built, and we've done 10 years of work on that.
Right, but I guess you also had another result there, which said that where physically you put these people actually mattered, right? So if you put them, it mattered whether you put them in the center versus the periphery, right?
Yes. So in addition to that, that experiment also included a topological manipulation where we explored where in the social group did you have to inject this AI. My lab is not a computer science lab. So in my lab, we're not trying to invent super smart AI to replace human cognition, like AlphaGo or AlphaFold or ChatGPT. We're not capable of, nor are we inventing super smart AI to replace human cognition. We are inventing dumb AI to supplement human interaction. And precisely because the human beings are smart, all you need to do is add a little bit of dumb AI, a little bit of catalysis into the social system, which unlocks the potential of the human beings to solve their own problems. Now, incidentally, this also does provide a model for the application of more complex forms of AI. So we show it with simple phenomena, all the more so with even more complex phenomena. But my lab is focused on the human-human interactions in the presence of AI more than in the development of the AI itself.
So if I understand this right, you're solving these sort of collective action kinds of problems,
Yes.
right? Where people have to sort of cooperate to solve this, and you're inserting the technology and saying, what are the best ways to insert the technology so
Yes.
that the collective solution that emerges is better?
Yes, and we solve a lot of canonical problems. So these collective action problems have many varieties. So, for example, how do we reduce tax avoidance? How do we get people to contribute to building a lighthouse? These are so-called public goods problems. How do we solve coordination problems? How do we solve evacuation? Like one of my principal collaborators in this work initially was Shirado, who is a Japanese, actually originally trained in computer science, and then came to my lab and did a PhD in sociology. Now he's at Carnegie Mellon. And Hiro was very interested in evacuation after the Fukushima disaster. How do you coordinate people to effectively evacuate? Or how do you foster creativity in groups? Like you have a group of engineers that are trying to invent something, or a group of people that are trying to innovate or preserve innovations. Are there AI tools you can add that don't so much do the innovation themselves, but facilitate the emergence of innovation and the maintenance of innovation in social groups? So we've done experiments with coordination, cooperation, evacuation, communication, innovation. All of these things we've shown in different experiments we can enhance with the thoughtfully programmed AI agents injected into the system in certain ways.
There's some other experiments you also did around negotiation and collective action having to do with simulating a game of chicken, for example. Say more about that, because I thought that was really interesting. And that has sort of all kinds of sort of interesting implications about when an AI intervention might actually lead to, when it might enhance outcomes and enhance trust versus diminish it.
So first of all, everything, in my group, I'm very happy to report that we have a very positive and optimistic outlook, and we're trying to use these ideas of human social interaction to make the world better. How do we increase breastfeeding in isolated villages? How do we reduce the spread of misinformation online? How do we try to reduce racism online? How can we intervene to make groups perform better and be higher functioning? Now, of course, every one of the things we do could be reverse engineered for evil purposes, to make every one of those things worse that I just mentioned. And but that's not explicitly what we do. But we are studying ways in which these introduction of AI agents into social systems can degrade our natural proclivities. Our natural proclivities to or abilities to solve collective action problems. So the example you gave is a good one. Let me play it out. So in that experiment, what we did is we had basically remote controlled cars, and we had human drivers that were driving these cars. Actually, they were recruited from around the world, and we built a little scale model of a highway in the laboratory, and they controlled these little remote control vehicles, and they played the classic game of chicken, which is that you're both driving at high speed to each other, and the first person to veer off is the chicken, and they don't get as much of a payoff that allows the other person to drive at high velocity all the way to the other end and win the race. The worst outcome is neither of them swerve off, and they collide, and then they both die, and they get no payoff. The second worst outcome is they both swerve, and so neither of them moves at high velocity to the target. And the optimal outcome is one of them swerves, but really, if it's a repeated game, that they take turns. First you swerve, and then I swerve, and you swerve, and then I swerve. So two humans put into a game of chicken very quick, if they know it's a repeated game, and if the payoffs are as I have described, will very quickly realize that the best outcome is if they take turns. I let you go past this time, you let me go past the next round.
By the way, Nicholas, you do realize that you're describing the road situation in India, don't you? I don't know if you've been to India, but you're describing that's exactly what you're describing here in the lab.
I have, and there's this game in India, like pedestrians, if I understand it's the same in the United States. You don't want to make eye contact with the driver because you persuade the driver that you don't see them so that he doesn't hit you. But it's a very dangerous game because he might not actually be seeing you and he will run you over and kill you.
Yeah. By the way, I don't know. Have you heard of the sociologist called Paul Hebert? He wrote a paper, I don't know, maybe like 30, 40 years ago, where he talks about, he describes the situation in India, the sociology of driving. And one of the things he says is you do not make eye contact because you don't want the other person to think you've seen them.
Yes, and that can avoid them. Exactly.
Exactly, yeah.
So,
anyway, sorry to interrupt. I couldn't resist that.
I've been to Mumbai many times. I was privileged to be the head of an alliance between Tata and Yale for a few years. And then so I've been to Mumbai many times, and then I went to Pune, and so we had the long drive from Mumbai to Pune, and I've had a taste of Indian roads, and I never saw an elephant on the road, but I definitely saw every other type of
But by the way, that's a relatively civilized part of the country. Like Bombay and Pune, they actually have rules that they follow. But anyway, continue. Yeah.
So we have these two cars playing chicken, and what we did then is we experimentally manipulated the simple kinds of AI that the drivers could have to supplement their ability. And in this case, it was deliberately very simple. It was either auto braking assistance or auto swerving assistance, collision avoidance. And what we found is that if you add auto braking assistance so that the cars, when they come near each other, brake, that allows the human beings to act on their natural predilection to cooperate and say, you know what, you go first this round, and I'll go first the next round. And so the humans evolve a kind of norm. You facilitate the emergence of a natural norm of turn-taking when you add a little auto braking assistance. On the other hand, if you added auto steering assistance, the humans got morally lazy. So the cars, they just would swerve past each other constantly. And they never found, or much less often found, the optimal solution, which was turn-taking. They just sat back and let the car do the driving. And then, in fact, when we turned off these types of assistance, the auto braking or auto steering assistance, we found that moral laziness persisted even after turning off the AI. So this very simple experiment, illustrated the principle that our natural ability to solve collective action problems actually can be degraded by artificial intelligence, that we may come to rely on these agents in a manner that effaces our ability to actually work together to solve problems. So again, this experiment illustrated, and we've done another experiment. So we did another experiment with Brian Scazzolati, the roboticist at Yale, where we used humanoid robots, and we made groups of three people and one humanoid robot that were each given a tablet computer, and they were supposed to solve a game which involved a very trivial game of laying railroad track from point A to point B from a set. Each took turns laying a piece of track, and they were working together to connect point A to point B, choosing from a set of tracks, curves, and straight pieces of track that were allowed. And then we sneakily contrived that sometimes the game was insoluble. They didn't have the right combination of right hand and left hand turns to connect point A to point B. But what we really did in that experiment, was we had the humanoid robot. We varied the the manner of speech of the humanoid robot. So sometimes a humanoid robot told dad jokes, really stupid, jokes that turns out, by the way, are cultural universal. Like tribes in the Amazon, the fathers will the kids will go, "Oh my God, my dad tells the stupidest jokes." They say, and in Greece, in India, in the United States, amongst the Papuans in New Guinea, they dads tell dad jokes. So we had these humanoid robots tell dad jokes, and what we found was that we could change the communication pattern among the humans by manipulating the manner of speech of the robot in a very trivial and simple way, and that the humans communicated more effectively with each other depending on little tweaks to how the robot spoke. So all of these illustrate the externalities, the exogenous impacts, that machines can have on human groups.
So are there like some general sort of takeaways from this, or does this mean that we just need to do the experimentation each time to actually figure out what works?
So I think we're still in the understanding of hybrid systems. I think we're still in early phases. I was part of a consortium of people led by Iyad Rahwan at the Max Planck for Human Development in Berlin. He spearheaded a paper called Machine Behavior. I think we are sort of where the zoologists were 100 years ago in understanding machine behavior and in understanding human machine system behavior. So I think there are some sort of fairly obvious high levels things you can say, which we've been talking about. That is to say that these machines can be programmed in ways that affect the collective action. That's a truism now. I think we have a lot of evidence for this. But subordinate to that, I don't think we have yet a lot of guiding principles. Like, experiment by experiment, we know things like, noise can help groups find optimal solutions. We discussed that, for example. But I don't think we yet have, a kind of deep enough understanding of this. But I think we are on the frontier of that. I mean, I think everyone knows that in the next 10 or 20 years, we're going to transition to a world where almost a futuristic world where there'll be humanoid robots in people's homes, and there'll be machine-driven cars on highways mixing with human-driven cars. And at checkout counters, there'll be human checkers and machine checkers. And all of these will represent a mixture of humans and machines interacting. And we're going to have to really get a grip on the ways in which these hybrid systems work as different from or as superior or inferior to human-only systems or machine-only systems.
Yeah, I think we're sort of really in the early innings of this, and this is something that business leaders are really struggling with, right? How do you really incorporate AI into work in a way that enhances productivity? And
it might degrade productivity, right? The workers, for example, here's a thought experiment. Imagine a line like at my local supermarket. When you were checking out, you can go to lanes that have a human, or you can go to lanes that have a machine where you do self-checkout and you just scan your things. And it's an interesting choice, okay? And from the point of view of me, do I want to interact with a person? Maybe I purchase some vegetables, or maybe I just want the real interaction with a human being, or I feel like there's something wrong with my credit card and I need to make sure the human being knows it, or I need to update my the customer number or something. Or do I want to use a machine and have a very impersonal, maybe simpler, maybe slower or more rapid, kind of interaction? Okay, fine. But now consider from the point of view of the human checker. This human checker might look around and say, oh my God, my job is being performed by a machine 2 aisles over. And either the human checker will feel degraded by this and reduce their performance to emulate the machine, for example, like no eye contact. Why should I make eye contact with you? The machine doesn't make eye contact with you. I don't need to make any small talk with you. The machine doesn't make any small contact with you. So they might come to emulate a machine in a kind of degrading way for both them and for the real human. Or conversely, they might say, wait a minute, I need to distinguish myself from this machine. I'm a real person. I'm going to smile at you. I'm going to make a joke with you. I'm going to say, can I help you with anything else? Did you miss anything in the store? Oh, you bought these peanuts. Did you know there's this other brand of peanuts that you can buy or whatever? So you can imagine the machine, the introduction of the machine into the system could either enhance the productivity of the humans or degrade the productivity of the humans. And I think a lot of that is going to be, I think some principles will emerge, but I also think initially, at least, a lot of this is going to be very bespoke. You're going to have to test it. If you're a business leader, you're going to have to test, what does adding these machines to these systems of humans. Now, if they're only machines, that's different, right? Like if it's an all-machine shop floor. But it's these hybrid systems that interest me and that we're talking about.
Yeah. No, fascinating area. So I want to segue over to your field experiments in Honduras, in the area of, influence, friends, smell. Yeah, let's take them in any order. There's several things you did in those studies. One was to sort of identify, key influencers if you want to make a difference. Another one was the study of friendships, and related to, genotypes. And then, on smell, which I thought was fascinating, about the sort of distance between people's genotypes and friends, which, sounds really interesting. So talk about these, any order.
Well, again, this was a sequence of ideas and a sequence of projects. So you alluded to earlier our work in 2007 on obesity. So we used the observational data from the Framingham Heart Study to show that you could have a kind of social contagion of obesity. So that as I gain weight, it makes my friends gain weight, which makes their friends gain weight, which makes their friends gain weight. So that we could trace out in that observational setting an impact of my weight gain on my friends, and friends, for example. And by the way, this also touches on something we also talked about, which is the excitement of being a scientist. And I think that was the first thing that I would describe as a discovery in my own life, that I had been working, and that was in my 40s, my early 40s. I'd been working as a scientist for a long time, but mostly I was sort of, replicating work of others or adding very small wrinkles to the work of others. But that feeling of discovery that I had in 2000, well, we published it in 2007, but I was aware of it in 2005, was just an extraordinary feeling. And we can come back to that and like what it means to discover. But anyway, that work was published and it elicited a lot of excitement, but also a lot of criticism. And I thought a lot of the criticism was unfair. I think people, were like, well, there's some problems with this work. And I was like, no, no shit. Yes, I'm quite aware of the problems here, but it was still a contribution. And we very quickly, because of the universal difficulties in making what's called causal inference with observational data, because with observational data, it's always very difficult to be certain about causation, we very quickly moved to doing experiments. In fact, we published our first experiment with social contagion in 2010, showing that we could induce cascades of cooperation in social systems. In other words, if I'm nice to you, you'll be nice to the next guy, I'll be nice to the next guy. In fact, we showed these ripples of contagion, of social contagion for cooperation out to 3 degrees of separation in this experimental setting, having previously shown it in this observational setting for obesity. Now we showed it in this experimental setting for cooperation behavior back in 2010, almost immediately after we did this. And it was very ironic to me because as is typical in the sciences, there's this fundamental trade-off between experimental control and realism. And so when we did the observational work, they said, well, how can you be sure about causation? And when we did the experimental work, they said, how can you be sure about verisimilitude? And so I'm like, well, take your pick. What do you want from me? You can't have both. And here we are building a body of research. So that move, beginning in 2010, inaugurated a program of research in my lab where we did experiment after experiment after experiment, field trial after field trial after field trial in Honduras, in India, in the United States, online, where we did all these experiments to show experimentally that we could induce social contagion, that we could create artificial tipping points of desirable behaviors in real populations. So our first experiment in Honduras was working in the Lempira region of Honduras, was published in the Lancet in 2015. But then, actually, even prior to that, we had begun a mammoth project supported by the Gates Foundation in the Copan region, where we created the biggest, or one of the biggest, mappings of human social networks, face-to-face networks ever undertaken. We mapped the face-to-face social networks in 176 villages in this isolated region of Honduras up against the Guatemalan border, over 30,000 people. And we repeatedly mapped their networks every couple of years. And we implemented a randomized controlled trial of different network targeting algorithms. So different villages were randomly assigned to get different systems by which we chose structurally influential people. And those people got a 2-year maternal and child health intervention to improve breastfeeding and cord care and timely response to neonatal emergencies and so these other development economics, public health practices. And then we studied everyone in the village, not just the people to whom we gave the intervention. So we tried to see what we were trying to measure is the response to treatment, not among the treated, but the response to treatment among the untreated. If I picked 5 out of 100 women in this village to educate them about breastfeeding, not what did they do, but what did every other woman in the village do? So we measured the outcomes in everybody in the village, not just the people to whom we gave the intervention. And with this, we were able to show, we published a lot of papers from this, but a key paper was just published in the journal Science in 2024, 2025. We were able to show that we could induce behavioral cascades. We could induce social contagion to optimize maternal and child health, creating these positive cascades rippling out from the women that we and others. They weren't just women. Everyone in the village was educated. We could induce social contagion at scale in this population. So that's the most recent mammoth experiment we've done. By the way, we also did an experiment in Mumbai with working with Tata Chemicals to foster the adoption of iron-fortified salt to reduce neonatal anemia and maternal anemia by encouraging women to purchase iron-fortified salt. And we showed that we could enhance that as well and create virtuous cascades where when one woman adopted this product, it made others adopt the product and so on.
So how did you find the people to target?
So we in these experiments, these are experiments. So we one arm typically is a control arm where people are chosen at random. So in many of in villages, we picked, let's say, 5% of the people at random, or 10% of the people at random, or 20 or 30 or 50, and so on. And so we did block randomization by village so different villages were randomly assigned to different targeting fractions. And once we had, okay, in this village, 10% of the people have to be chosen, they were chosen at random within the village. And in another arm of the experiment, we exploited this old, again, going back, we've been studying this for like 10 years. We exploited an old finding in sociology known as the friendship paradox. So just to set the stage, if you're going to use network targeting to enhance the adoption of desirable properties in groups, you want to invent a method, or we wanted to invent a method going back 20 years now, that didn't require mapping the network of the whole village. Like if I invent something that's good for development economics or good for global public health, but every time you need to do it, you have to go into a village and painstakingly map the social interactions in order to identify structurally influential people, nobody would do this. It'd be hugely expensive. So we needed to invent a method that you could identify these structurally influential people within a network without having to map a network. And to do this, we exploited something called the friendship paradox. The friendship paradox is an old finding in sociology which says that your friends have more friends than you do. Turns out this is a universal property of social networks. If you pick people at random and have them nominate their friends, say, okay, here am I, you pick Susie, and Susie says Tom, Dick, and Harry are her friends. Then you pick one of those people at random, either Tom or Dick or Harry. Tom, Dick, or Harry, on average, will have more friends than Susie. And so what we do is we go into these villages, we pick 5% of the people at random, we say, who are your friends? They tell us, we pick one friend for each of those people, and then we deliver the intervention to that 5%, the friend of the random people. And then we showed that actually it works, that giving it to that 5% has a much a discernibly bigger effect on the global adoption of the product. And so
relative to the control group. Yeah.
Yeah. And so this is a trick that you can do now. You can roll this out around the world. Or if you're vending products, you could do it in marketing as well. Or if you're trying to increase adoption of practices in schools or in hospitals or in firms, you can use these ideas to accelerate adoption in these social systems. So we've done many experiments now with friendship nomination targeting, field trials, a couple of mammoth trials in Honduras, in different parts of Honduras, a big trial in India, and some online trials as well, in the United States, all of which have documented the efficacy of this trick.
Fascinating. So let's talk about smell. Your study of friendships that are related to olfaction.
So in 2010, my then collaborator, James Fowler, who's a political scientist in California, James and I had been working on the Framingham Heart Study, and we became very interested in the evolutionary origins of friendship. And if you think about it, and I've since written a book, I wrote a book called Blueprint, The Evolutionary Origins of a Good Society, which was published in 2019. Friendship is a very unusual phenotype. Friendship is the long-term, non-reproductive union to an unrelated conspecific. So the volitional, long-term connection to an unrelated conspecific is what is a friend. And so we, like other animals, mate with each other. We have sex with each other like other sexually reproducing animals, but we also befriend each other. And this is very rare in the animal kingdom. We do it. Certain other primates do it. Elephants do it. And certain cetacean species do it. And so the question is, why? Why did we evolve this rare phenotype, this capacity to have friends? It must enhance our fitness in some way. And so I set out to sort of answer this question and began a body of work looking at the evolutionary biology of friendship. Now, here, there are many other scientists working in this area, to be very clear. But in my group, we began to study this in earnest. And our first paper that I published, as I said, with James in 2010 in the journal PNAS was a paper called Friendship and Natural Selection. And in that paper, we showed that when people were given the choice of who to befriend, if I gave you 1,000 people to choose from, you would tend to pick as your friends people who resembled you as if they were your third or fourth cousins. Now, they are not your third or fourth cousins, to be very clear. And we had the genotypes for these people, so we could show that you shared with your friends something called identity by state, not identity by descent. In other words, if I genotyped you, Vasant, and your friends, even after accounting for the fact that they're more likely to be Indian, like my friends, let's say, are more likely to be Greek, it's no shocker that I might genetically resemble my Greek friends. After taking that into account, that like I might have some, let's say, ethnic similarity with my friends, even after taking that into account and after excluding from my list my actual cousins, that the people I chose as my friends would weakly resemble me on a genetic level. And this makes sense from a whole body of research known as kinship selection in evolutionary biology, where we tend to try to, listeners have probably heard that, you would sacrifice your life for 2 of your children or, 8 of your cousins and so on, that people would have gain a kind of Darwinian advantage from assisting individuals who were actually their cousins. But when you pick friends, the system may go haywire, and you may wind up picking individuals who are not actually your cousins, but resemble your cousins. Is the argument, I'm moving too fast, but that's the essence of the argument advanced in that paper. And in that paper that we published in 2010, we also discovered that if you look deeply at the regions of the genome in which you resemble your friends, we found that people were homophilous, resembled their friends on what's called an olfactory gene ontology. In other words, on a set of genes related to olfaction. So we found that people tend to pick as their friends other people who smell the world similarly to them. So you have,
is it so? Is it like who smell the world similarly to them, or who smell like them?
it's olfactory, not
Yeah.
not odor. So what we found is that it's not that they smell. It's not that the odor they emit is similar to their friends. It's that their perception of the world. You hate coffee. You find coffee repulsive, and I find coffee repulsive, and that's why we're friends. So that little finding was parked there, but it was in my mind for 15 years. I was obsessed with this. And it took a long time to be able to build the laboratory capacity to study this. And so we embarked on a project to start looking at human social chemosignaling, which we've now begun to do with support from the Nomis Foundation in Switzerland. We've now begun to study the odors we emit and our capacity for olfaction and the odors that we smell and that we like. So
interesting. So how did you measure that? How did you measure people's sort of similar affinities to?
So there's standard. So there's those are some standard ways to do that. But let me just frame for listeners another idea before we get to the specifics of what we're doing. And I can't really discuss the results of what we're doing yet, but I can tell you the kinds of things that we're interested in. So this is a work done by another lab, not our lab. You know that intoxicating smell of a newborn. You know, when you hold a newborn baby and you put your nose in their scalp and they smell divine, right? That newborn is just such a good smell. It turns out that a key constituent of newborn baby odor is a chemical called hexadecanol. It's an 11 hydrocarbon chain with a little aldehyde group at the end. It's an odorless constituent. So this other experiment, they took hexadecanol and they exposed men and women to hexadecanol, and then they measured, or saline, and then they measured the serum testosterone. They drew blood from these people and they measured like what smelling hexadecanol does to your testosterone, and they measured their propensity to aggression. So they looked at how the people behaviorally would act when would they blast a loud sound to punish someone in this sort of behavioral model. Anyway, and what they found is that men exposed to hexadecanol, it makes their serum testosterone go down and their aggression go down. And women exposed to hexadecanol, it makes their serum testosterone go up and their protectiveness go up. So we humans evolved such that when we are in our most vulnerable newborn state, we emit a volatile compound that floats through the air and reshapes the social behavior of other humans around us in a way that enhances our survival. So this little example that I've given suggests that we human beings use our odors as a form of communication. And furthermore, that the perception of odors may have evolved in parallel with the emission of odors in ways that are relevant to our formation of affiliative, such as friendship, ties. So some of these ideas are discussed in my book Blueprint, but this is now an area of considerable excitement for me in my lab. So we are beginning to study human social chemosignaling, and we are using the long-term site that we've been working in Honduras that the Gates Foundation supported, that the randomized trial that I told you about that began 10 years ago with 176 villages. Now we're using like 20 or 30 of those villages as a site to study the biology of human social interaction. And we also have been doing work on the human microbiome, which actually we've completed most of that work. We published a series of papers on how the microbiome can spread from person to person in the networks. So that the microbes within your body.
Yeah, say more about that. By the way, I want to make sure you sort of don't just skip it, because I thought that was interesting. My takeaway from that was that we have our biomes are similar to are sort of proportional to sort of distances in the social network.
Yes. So unsurprisingly, the microbiomes in and on our bodies resemble the microbiomes in and on our friends' bodies. And the microbes evolved to exploit human social networks as their environment. Like these microbes in your gut, from their perspective, the world is the social network. That's the world they live in. And anything they can do to facilitate spreading from person to person would be good for them, to exploit, let's say, friendship connections. And what we showed in that work was, and this work was published, the most recent paper was published in Nature in 2025. What we showed in that work was that we were able to document using detailed metagenomic or detailed study of the genes of hundreds of microbes, was that these microbes are shared between individuals within the social network and appear to spread from person to person and person to person to person and person to person to person to person. Now, the reason that's relevant, or not, it's relevant in and of itself, but the vistas that opens up is the following. So other laboratories have shown that the microbes in you can affect risk for various things that people may not be aware of. For example, the microbiome in your gut may affect your risk of depression because it metabolizes certain neurotransmitter precursors in a way that flows across your intestinal lining into your bloodstream and then spreads to your brain. So you might be depressed in part because of the microbes in your stomach. Or it affects your risk of obesity, so that, for example, unsurprisingly, the microbes in your stomach may digest carbohydrates differently, and the way they digest carbohydrates may affect how fat you are. Or it can affect things even like your arthritis risk or your hypertension risk. So there's all these other labs that are doing this work that shows that the microbiome in your body can affect the risk of all these chronic conditions: depression, obesity, arthritis, hypertension, diabetes, and so on. My lab has shown that the microbes can spread through these social networks. So what this combination of these ideas opens up is the realization that a whole host of diseases formerly thought to be non-communicable, like obesity, depression, arthritis, and hypertension, might actually be communicable via the spread of the microbiome. So it's not just things like, COVID or cholera that are communicable. Things like cardiovascular disease and diabetes and mental illnesses might be communicable. And so our work has helped support some of these claims. And we've been publishing a lot of work on the microbiome and are continuing to work in that area. But then again, as usual, once we were doing that work, we then got interested. And once we had this old result from chemosignaling, from olfaction, I was like, okay, there's a whole new thing we can do, which is also because the microbiome also helps contribute to your odor. Your body odor in part depends on the microbes in your stomach and in your mouth and on your skin. The microbiome is a key driver of your body odor. So I said, we need to study human olfaction. And that got us started on that. And then that in turn led to a body of work, because in order to assess odors, basically one of the scientific frontiers is to use artificial intelligence to quantify this very high dimensional and complicated thing called odor. So that then led to some work, and we've just been starting to release preprints on AI and odor from my lab. Anyway, so we're talking. There's too much to talk about. I mean, there's just so much science to do. I mean, there's just so much stuff to do that it's just a super exciting moment in the lab right now.
Indeed. I think we could set up an entire session just to talk about smell. There's so much to say in that. But that was fascinating, that the fact that the biome is not just a function of the environment, but it's the environment plus the social network, right? I mean, that's what's like really interesting.
But see, Vasant, it had to be that way because the bacteria in your stomach have evolved for the anaerobic conditions in your stomach. So where did they come from? How did the bacteria in your stomach get there? Of course, when you're an infant, they come from your mother. But in adulthood, how do they colonize you? These bacteria can't survive outside the body very long at all. They don't come from surfaces. They don't come from the environment. I mean, some do from yogurt and stuff like that. They come from other people. So it's physical contact between people, between you and your family and you and your friends, that is contributing to the microbiome in your body. And in fact, when you use antibiotics and you wipe out various species in your body, you're recolonized by your friends, actually, by the microbes in your friends. And it has to be that way. So it's kind of obvious in retrospect, but it's very difficult to show. Anyway, we were able to show it.
Yeah. No, fascinating. Well, Nicholas, this has been a fascinating conversation, but I feel like we're just getting started, to be honest.
Well,
so I'm going to have you come back on and get into some more details, especially around smell, which is something that, I've been studying for several years as well. So
yeah, I mean, I would love to talk to you again, but I don't want to leave without also pointing people to, because we've alluded to some of these things during the talk, to our new vlog we have on YouTube. We have a vlog called For the Love of Science, which is part of our science outreach effort in my lab. And the handle is at NA Christakis. Maybe you can add it to your show notes or something. But it's in that vlog, we make little videos that we release every week. And what prompted this is the kind of my perception that we have a problem right now, not only in our society, but worldwide, in the rise of kind of unreason and a rise of kind of authoritarianism. And I think as scientists and as citizens, we have a duty to kind of push back a little bit at this increasing ignorance, I would say, and conspiratorial thinking, and to try to enhance the public understanding of science. But what we're attempting to do in that vlog is not so much focus on the content of science, but on the practice of science. Like, what is it? What is science about? And so we try to talk about things like the feeling of discovery that we talked about earlier, or how scientists pick research topics, or what to do if you're a scientist and your work is abused, or if you're practicing or you're a young scientist, how do you ask for a recommendation letter, or how do you write an email that gets a response from someone? And so it's about the practical aspects of science. And and what motivated this vlog is the kind of sentiment that we need to help advance the public understanding of science. Anyway, we release videos, short little videos every week on different aspects of the craft of science. And anyway, it's a new initiative in the lab that I'm eager to make people aware of.
Yeah, no, thanks for mentioning that, because I did watch several of those. They're really good, really well done. I saw the one about about the letters. I also saw the one about you going to Ukraine and doing your lectures there while occasionally you would have sirens and have to seek shelter. That was really moving. So thanks for mentioning that, and that's good stuff. Thanks for doing that.
Thank you so much, Vasant, for giving me this opportunity to talk to you and to share some of our work. I'm very grateful.
Thank you. Thank you for your time. Thank you for sharing your ideas and these studies, which I think are fascinating. And we will talk again.
I look forward to that.
Yep, likewise. All right, take care.